These loops, the length of the nephron, determine how concentrated the urine can be without the use of excess ATP. So it determines how much, if you have to get rid of, and let me say, we're only going to talk about sodium and water here. I had this student, Hugh Ngao, who worked in my lab a while ago, and he took my class, and he's a doctor now. And several years after he graduated, he sent me this Facebook message, said, there's a lot more to the kidney than you taught us. For the purposes of this class, we're going to talk about sodium and water regulation. You're regulating waste and urea and chloride and potassium and all kinds of stuff. We're only going to talk about sodium. So don't be emailing me from med school talking about all that stuff out. I can't cover it. I am but one man. This is one class. I can only cover one thing. But the length of these loops of the nephrons determine how concentrated you can make your urine. So, for example, if you looked at a whale or a desert kangaroo rat, a whale has no problems getting sodium. It lives in the ocean. It needs to conserve water. It needs to make concentrated urine. So you have a huge renal pelvis with really long nephrons. So if you're a kangaroo rat or a whale or a dolphin, something that really needs to conserve water, you have really long nephrons and loops of Henle. But again, I think that comparative evidence demonstrates how important the loops are. Non-mammals don't have them at all. Birds have a few, but they're not in parallel. If you really need to conserve water, you have huge long ones. And if you're like a beaver or a nutria, who knows what a nutria is? Just in Trinidad, sorry. Then you have a short renal pelvis because you live in fresh water, and so getting fresh water is not a big deal. You don't have to make concentrated urine. So the loops and the length of the nephron, the length of these loops, are incredibly important. And it's these loops that make you able to make concentrated urine, to not waste water. Because once you live on land, you can't waste water. And remember I told you aldosterone was the hormone that made it necessary, that made it possible for terrestrial life. It's also only one of two vital hormones. You cannot live without aldosterone. The other one is parathyroid hormone that we'll talk about on Tuesday. So the sodium So what we're going to talk about now, actually for the rest of the class, is the osmostat. Last time we talked about the glucostat. And actually when I was walking here this morning, I realized I'm not sure if those are real words or if I made those up. But I figured thermostat, you regulate temperature, glucostat, you regulate glucose, osmostat, you regulate osmotic pressure. And on Tuesday we'll talk about the calciostat, when you regulate calcium. But I may have made those words up. So maybe don't use them outside the class. I'm not sure or not. But the osmostat, and write this down. The osmostat is how you regulate osmotic pressure. And you will do so by regulating both sodium and water. And it looks something like this. And write this down. We're going to do it kind of the way we did the glucostat. If sodium goes up, aldosterone, as you'll see, goes down. If aldosterone goes down, sodium goes up. If sodium goes up, aldosterone goes up. And if aldosterone goes up, sodium goes up. Did you write that down? Yes? Did everybody write that down first? Did I write something wrong? If sodium goes up, aldosterone goes down. If aldosterone goes down, sodium goes up. Sodium goes up, aldosterone goes down. You got it written down? So if sodium goes up, this is true. If sodium goes up, aldosterone will go down. If aldosterone goes down, sodium goes up. If sodium goes up, aldosterone goes up. Okay. Oh, sorry, sodium goes down. Anyway, it doesn't matter because cross this out because it ain't true. But I'll tell you why people used to think that. Thank you for it. I knew something was wrong. Even as I was saying it, I knew something was wrong. But it's not true. Anyway, we'll spend the rest of the day figuring out why it looks like it's true, but it's not true. Let's do the nephron first. That was a test. I did it on purpose. Make sure y'all was paying attention. So if you look at the kidney, the unit of the kidney are these nephrons. These lines that I've drawn here, and they're all in parallel. And remember, I have limited artistic capabilities. So I'm going to do the best I can. I'm going to show you some pictures on Thursday, but work with me today. The blood enters each one of these nephrons in the same way as it does in other vertebrates. Now coming through the afferent, and it comes through these, what's called the glomerulus. It comes through these very small blood vessels. And that increase in pressure as they come through these small blood vessels generates, I feel like there's an air of suspense, generates an ultrafiltrate. So everything that's small gets pressed out. And here are the parts. It's going to get pushed into something called the bone. I'm going to put abbreviations, and I'm going to write the real things over here. Okay? Oops, that's fine. Now, here's what these things stand for. So the blood comes through the afferent. You generate this ultrafiltrate, and the ultrafiltrate is going to go through the Bowman's capsule. Named after some guy named Bowman. And the Bowman's capsule, I brought one. So this would be the proximal proximal convoluted tubule. The Bowman's capsule is like a Bowman's capsule is literally like a bag. So that if this is my glomerulus, bag is like this. The glomerulus is the bag is kind of wrapped around. Can you guys? Okay, maybe that looks kind of weird. The bag is kind of wrapped around. The glomerulus is like in there, right? So this is my glomerulus, and the bag, the sac, is kind of wrapped around the glomerulus. So this ultrafiltrate. Should I pass this around? Anybody want to see this? So this fits into the bag. The ultrafiltrate with all the small molecules, we're going to do this in a minute, is pushed through the Bowman's capsule. It's pushed out of my fingers, and this bag is a membrane, and it goes across the membrane. Oh, those are more like sodium channels. So the bag, again, you can't buy these. I make these things just for you guys. So the ultrafiltrate is coming through my afferent. It's pushed out because of the hydrostatic pressure here. The ultrafiltrate goes out, it ends up in the bag, the Bowman's capsule, and then it goes through first, the proximal convoluted tubule. So it's the proximal means close to. So it's convoluted means how one of you guys said I lecture sometimes. It means like kind of twisted and curvy. So it goes through the closest convoluted tubule. Then the filtrate, which will become the urine, will go to the thick descending loop. Then it will pass through the thin descending loop. LOH is the loop of Henle. You got the guy named Henle that described it. And then it goes up through the thin ascending loop, then through the thick ascending loop, and finally then through the distal convoluted tubule, and finally through the collecting duct, and all these collecting ducts will end up emptying into the ureter. So in much the same way, like if you think about the testicle, right? There were all these testicular tubules, they all ended up and this retestis, which all ended up in the epididymis, which all ended up going through one vas deferens. So you have a whole bunch of tubes that ultimately end up combining at the collecting duct and emptying into the ureter. And then to the bladder and then out when you urinate. We're good so far?
So the CT collecting duct or it goes from the CT to the collecting?
No, CT is the collecting duct. I didn't have room to write it on the other board. And there's a whole bunch of collecting ducts that all end up in the ureter. So you have a whole bunch of, I'm making a number, 100,000, a million, I don't know how many it is. It makes the kidney crunchy when you eat it. There's a whole bunch of these all lined up, making concentrated urine, depending on your situation. And then they all end up in the ureter. They all dump into a collecting duct, the collecting ducts all end up into one ureter. But different things are happening to the urine, or the would-be urine, as it goes through that structure. But we're going to have to take a time out and talk about something else before I give you the answer. We're good up to here? This is just anatomy, so we haven't done it yet. We haven't peed yet. We're good? No questions or comments? We'll move on? Okay. Go. Keep your eyes step now. We're going to work on that. As you go through the nephron, the membranes in the different parts of the nephron are very different, and some of them are regulated, so some of them change. We're good? Let's talk about membranes. I know some of you guys have had this. Give the rest of us a break. Some membranes are impermeable. So some membranes could care less what's next door. What's on the other side of the membrane? We might not get the people, but we'll get it. So imagine I have a vessel. And the vessel is divided by a membrane that's impermeable. That means that neither water or solutes, solutes are the things dissolved in the water. That means that neither water or solutes can go across. So, and size matters here. So this has more concentrated sodium than this side. But the membrane doesn't care. The osmotic pressure would be different, but the membrane is impermeable. And I can measure the osmotic pressure hold off on that for a second. Let's be better explained right here. If you have a semi-permeable membrane, a semi-permeable membrane. Semi-permeable means that water can go across, but the solutes can't. So that means that in this situation, the osmotic difference, I'm going to do water in blue. I know you won't be able to see it, but somehow it seems like water should be blue. We're good? No, you. So, can you guys see that? Can you see it? Say, raise your hand if you can't see it. Oh, okay. So, in this case, the osmotic pressure is different. So the water can move. The water wants to balance the concentrations. Does that make sense? So the sodium can't move. It's semi-permeable. That means only water can move. So you guys can see that, really? Am I that old and my eyes that bad? Because I can't see nothing. It just looks like a blue blob. But the water wants to go across due to the osmotic pressure difference. And you can measure osmotic pressure. Because if you have I don't know what this is called, a little thing over here, how hard you have to push down to stop the water from moving is a measure or an estimate of the osmotic pressure. So you can apply hydrostatic pressure, the amount of pounds that I have to push down to stop the water from moving across is a measure of the osmotic pressure. On the other side, if you're an impermeable membrane, there's no difference because the membrane won't let anything across. It could care less how much solute and how much water is on the other side. Does that make sense? Yeah? Order 9. Then there's something called a selectively permeable membrane. That creates kind of a different situation because in a selectively permeable membrane, the water can go across, but also they're channels that allow some solutes to move and some not. So you can alleviate the osmotic pressure by allowing the sodium to leak across. Does that make sense? We're good? Because I want to at least pee once before we leave today. You guys can really see that blue? Wow. So here's why this is important. When we start to talk about the nephron. What if we have protein on that side? The vessel doesn't care what the solute is. The vesicle doesn't care, the nature does. So if you have a big protein, the protein, because it's selectively permeable, the protein can't move, but the sodium can. So you may be able to get more sodium or you may be able to maintain the sodium on the right side in a situation like this, simply because the protein is generating the osmotic balance. So in fact, you may even, depending on the relative concentrations, you may even get sodium to move across its gradient because the protein can't move. And all the osmotic pressure cares about is that there's an equal number of solutes, an equal number of things dissolved on each side. It can even be gas. Who has one of those things called where you can carbonate water? And they say do not carbonate juice? SodaStream, right? So there's a reason why if you carbonate wine to try to make champagne when your friends are coming over that it explodes. Because it doesn't even care if the solutes are solid. It can be a gas. It's measuring osmotic pressure. Ignore the solution. So for a selectively permeable membrane, you can have proteins sort of balancing out big things, or things that are not permeable across that membrane, balancing out, and you can even make ions move against their individual gradients. All right, questions? Again, I know some of you guys have had this in physics, 8A or 8B, whatever it is, chemistry. We're good? Okay, let's go back to our nephron. I'm going to draw another nephron. Remember your different types of membrane. Okay, so your blood comes in, you generate this ultrafiltrate. You apply hydrostatic, am I good? You apply hydrostatic pressure so that you force all small molecules out. Again, we're only going to focus on sodium, and glucose. But you force all your conjugated steroids, your urea, your chloride, your potassium, your sodium, your bilirubin. I almost named my son bilirubin, but my that's a cool name, right? My wife wouldn't have it. She let me name my daughter after frog, so I guess kind of worked out. We're going to focus on sodium glucose. So you force out all small molecules. The protein, though, doesn't come out. It's selectively permeable. And somebody always asks me, because if protein's in your urine, it's bad. It means you have kidney damage. Somebody always asks, well, how come there's so much HCG in urine? And I have no idea what the answer is. Ask Tom Carlson, see if he knows. I don't know. I know he don't know because I asked him. So I have no idea how all that big HCG, because it's a big glycoprotein. I have no idea how it gets there, but you're not supposed to have protein in your urine. I think unless you have like a bacterial infection or kidney damage or something. So the small molecules come out. It's an ultrafiltrate. We're going to talk about sodium and glucose for a minute. Because in the proximal convoluted tubule, the PCT, okay, I'm going to erase this. We did membranes and now we're in the nephron. We probably won't get to regulate sodium today. We'll do that on Thursday. So you just have to hold it. Who can tell what that is?
A cross section of a vessel?
See? You get some extra points. Oh, not a blood vessel, a proximal convoluted tubule. So imagine I've cut this tube in half. I've used my artistic abilities to show you what it looks like. It's one cell thick. The cells are highly polar. I didn't say polarized, they're polar. In that what's called the apical or the mucosal side. So this will be the side inside the tube. So I'm going to go ahead and pass this around so you can see exactly what I'm talking about. So this is your proximal convoluted tubule. And see this section at the bottom? That's the cutaway. Back me up. Looks just like I don't. That's the cutaway. Okay? And this part, the cells, the side of the cells that are inside, don't stick it inside because there's thumbtacks in there. Don't cut yourself. I won't be liable. So the inside, that's called the mucosal or the apical side. Go ahead and pass it. The outside, this part, the part that faces the blood, the part that faces the blood is called the basolateral or the serosal side. And they're very different throughout the nephron. We're good? So I'm going to blow up one of those cells for you. So this is the side that's inside the tube that's being passed around. This is the side that's facing the blood. We're good? So you've made this ultrafiltrate, and assuming you don't have diabetes, you should have very little glucose in your blood. I'm sorry, in your urine. Assuming you don't have diabetes, you should have very little glucose in what's now in this ultrafiltrate. Because insulin should have done its job from last week, assuming you're not diabetic. But there will be some glucose, amino acids, and things that you want to recover. It's difficult to recover the glucose because there should be very little. There should be more glucose inside the cell, right? So the proximal convoluted tubule, remember the sodium iodide symport? The proximal convoluted tubule has a sodium glucose symport, and it uses the sodium gradient to bring glucose against its gradient. So you recover glucose, amino acids, I don't know, vitamins. through specific symporters that utilize a symport. Wait, what did I just say? Does that make sense? Sometimes I hear myself say stuff and I'm like, what did I mean? The symport utilizes a symport. Is that what I said? Okay, well, you know what I mean. So it's a symport that's utilizing a sodium gradient to bring other things in that it doesn't want. Because see, otherwise, the glucose, think about diabetes. Think about diabetes. And think about wanting to do better on the next midterm. When I say think about diabetes. So if you're not diabetic, there's not that much glucose, but you want to recover it. If you don't recover it, otherwise the glucose goes on through your pee out. And you have sweet urine, like Anne demonstrated. Oh, I had to read I will respond. Sorry, I was inside of the country. So you recover it, but if you keep doing that, the problem is sodium will build up, right? So on the other side, on the basolateral, the serosal side, on the other side, it costs you. You have the old sodium potassium ATPase that's pumping sodium out against this gradient. And pumping potassium in against it. Right? And somebody correct me, right? It's 3 sodiums for every 2 potassiums for every 1 ATP. Right? 3 to 2 to 1. Right? Yeah. If you guys don't say anything, then it's going to become true.
Okay.
So on the other side, you're maintaining that gradient because you're pumping sodium out, bringing potassium in against its gradient, burning 1 ATP. And it's important to maintain that gradient, otherwise you can't recover the glucose. We're good? That's the first thing that's important. Think about how diabetes is different. Yeah, what's up? What's your name?
Lee.
Lee, what's up?
Which one's against its gradient?
Both are against their gradient. So the ATP is pumping 3 sodiums out for 2 potassiums in, both against their gradient. That's why it costs ATP. So it's an ATP-driven antiport. Is that what it is? Must be true. Nobody disagrees. So it's an antiport that's driven by ATP. So in both cases, you're going against the gradient. But you have to do that, otherwise you can't recapture the glucose and amino acids and other things that you need to recapture. Because those things should be low in here. Okay, then, so the glucose gets conserved. Then now here's the tricky part. Then the sodium and other ions, we're only going to talk about sodium now. The sodium becomes more and more and more and more concentrated. And I don't care if you can see it. I'm going to draw the water in white because I can't see it. No, I'm going to draw the water in yellow. That way we can both see it. Both yeah, yellow water. So the sodium is going to become more and more concentrated. So you want a second. Because the descending loop is semi-permeable. Just trust me for a second. The sodium is going to become more and more concentrated. Only mammals can do this. Because the descending loop is semi-permeable, so the water is coming out. And the water's coming out, you gotta make this move in your head. Because as you go up, the ascending loop is semi-permeable. So more and more sodium's coming out. So the water's coming out of the descending loop because the sodium's coming out of the ascending loop because they're moving in opposite directions. That's why they call it the countercurrent multiplier. And then as you go down the collecting duct, and only mammals can do this, as you go down the collecting duct, the sodium becomes more and more concentrated because the water's coming out to meet the sodium that's coming out of the ascending loop. And then the water gets taken up in the efferent because it's got a high osmotic pressure because it's still got all that protein in it. Let me let you think about that for a second. You have to imagine everything in motion to make this work. So I'll go through that again. Should I? Or shall I? The afferent comes in and squeezes out all the small stuff. Not all of it, but a lot of it. You recover at the proximal convoluted tubule, you recover all the stuff you want, like the glucose. Remember, insects, they can only take out certain things. We filter out everything, and then we recover what we want. That allows us not to be, well, you can still get poisoned, but that allows us some protection against toxicity, because you can filter out small molecules that are not natural. As you go down the descending loop, the sodium becomes more and more concentrated because water is leaking across the semi-permeable membrane. Why, you say? Water is leaking because a gradient's being generated because sodium is coming out of the selectively permeable membrane as you go up. As you go back down, the urine's becoming more and more concentrated because water's coming out to meet the sodium that was coming out when you went up. So there's a gradient this way that generates a gradient this way, and you have to make all those things move to make it work. What's up, Maggie?
Can you repeat that again, but a lot slower?
Sure. but now I chew all over. That's a natural question faster. So you generate the ultrafiltrate. What you want to do, you're my daughter. Probably not really. Maury says so. You're my daughter. What you want to do is you want to save as much water as possible, right? So you don't want, and you want to save your glucose. So first of all, you save your glucose because daddy's not feeding you because you got to learn how to act. So first you want to save your glucose. You understand how to do that, right? Oh, you say go slower, huh? Okay, so then you have the ultrafiltrate, which has a tiny little sodium. But as you go down, the sodium's becoming more and more concentrated as the would-be urine goes down the tubule. It's becoming more concentrated because water's coming out, which doesn't make any sense, except that as you go up, sodium's coming out to meet the water. So you're generating what's that called? Lateral? That lateral gradient? So you're generating a lateral gradient. The water's coming out to meet the sodium that's coming out of this side. So your sodium's getting more and more concentrated as you go down because more and more water's coming out. More and more water's coming out because as you go up, more and more sodium's coming out. So the water coming out depends on the sodium coming out. When you get up here, the sodium's now very low concentrated. But as you go down, the collecting duct, it becomes more concentrated because water's coming out to meet the sodium that was coming out when you went up. So you end up with concentrated urine. Other vertebrates can't do that because they don't have these countercurrent flow. They don't have these loops that bend. Birds can do it because they have isolated loops. Mammals can do it even better because the longer the loop, you see that why I showed you the comparative thing? The longer the loop, the more concentrated you can get. And the more loops, the more nephrons you have stacked in parallel, the more concentrated you can make it. Yeah?
Is the same amount of sodium leaving the line as you go up?
It's the same amount of sodium leaving. Depends on your situation. So if I answer, what's your name again?
Nelson.
That's it. So it depends on your situation. If I understand your question right. For this part is not regulated. This part's happening all the time. What's regulated, if you get dehydrated or if you drink too much water, what's regulated is how much sodium comes out here and how much water comes out here. And that's what the hormones regulate, which we'll spend Thursday talking about. So the answer is yes. If you look in any book, they'll say how many millimolar of sodium or whatever is moving. This is not regulated. That's always happening. What's regulated in terms of how much sodium and water ends up in your urine is the distal convoluted tubule and the collecting duct. How much sodium comes out here and how much water comes out of the collecting duct. That's what's regulated. But the ascending and descending, or the descending and ascending aren't regulated. That should be happening all the time.
So is that the same type of tissue, the same type of membrane throughout the loop?
So when you go, it's a good question. So when you're going down the loop, it's semi-permeable. It's only permeable to water. As you're going up the loop, the ascending, it's selectively permeable. The distal convoluted tubule is selectively permeable because it lets sodium out. But how much sodium it lets out is regulated. The collecting duct is semi-permeable or impermeable. If you get drunk, it becomes impermeable. That's why you pee so much.
So there wouldn't be different amounts of the sodium channels in the ascending?
That's correct. That's not regulated. What's regulated is the distal convoluted tubule. What's regulated is how much sodium and how much water comes out of your urine. And that's regulated by the distal convoluted tubule, and it's regulated in a very coordinated way, and in the collecting duct. The ascending and descending aren't really. I think the top part of the descending is regulated a little bit, but most of the regulations in the distal convoluted tubule and the collecting duct. The first part always happens. Other questions? Does everybody get it? Does it make sense or not? It won't make sense on Thursday. Trust me. Yeah.
It's probably a very easy question.
There's no stupid questions.
Where is the water coming from in the collective duct?
Where's the water coming from the collect? It's the water that you ultimately it's the water that you ultimately filter out. So you've lost some water here. It's not completely lost, right? You're not like peeing junk. It's not completely lost. Okay. So here's the last thing I'm gonna say. Where was my hospital? Here's the last thing I'm gonna say. If you remove the adrenal gland, you can no longer regulate sodium and you die. You can no longer retain sodium and you will die very quickly. However, the reason that this osmostat is not correct is because the adrenal gland has no idea how much sodium you have in your blood. But we'll figure out why I drew it this way on Thursday, and then we'll talk about how it really works. But I can show you experiments that will make you think that that's how it works. And that's where we'll start on Thursday. All right? I will be in office hours 8:30 to 9:30. If you need a different time, let me know. If you want me to come earlier, let me know as soon as possible. It takes me a long time to get here in the morning.